Okay, good afternoon. This is going to be our third lecture. And I think you guys download my lecture note already. I will follow the lecture note on the first part. And later, I will change to the extra example. Let me start by talking about the learning objective. When we study the subject of the inference line, and we start with the inference line diagram of statically determinate structure. The statically determinate structure, especially the beam, is a kind of, for example, the pre-stresses concrete beam. Okay, in that manner, when we draw the inference line of the beam, we use the Maxwell principle, in which we set up the 1.0 unit load at the position of X, okay, and by the Maxwell, the inference line diagram can be drawn like this. First, for example, let's say this is the point A and this is the point B. If you prefer to draw the inference line of point A, you just draw the beam and then you release the ability, the resistance of A sub y out. So this is going to be inference line of A sub y. You take the A sub y out. When you take the A sub y, the support here going to be the roller. The support here will change from the pin. This is the pin. Pin has A sub x and A sub y. When you release the A sub y, there still be the A sub x. So the pin over here change to the roller in this direction. And this is going to be the same roller here. What happened is you apply the A sub y and move it by 1.0 unit. And then the shape of this beam will change to the dashed backline. This is the inference line of A sub y. What the meaning of inference line? What the meaning is represent the reaction of A sub y when the force move. For example, when the force move to the point A, 1.0 here. The reaction here is going to be 1.0 cos to this. Okay. And when the force just move to halfway, 1.0 halfway like this, the reaction here is going to be 0.5 and the reaction here is going to be 0.5. For this one is 0. And when the force move to this position 1.0, the reaction here is going to be 0 and the reaction here is going to be O. What we plot over here is the reaction that's occur, okay, when the loads change. For example, when the load is here, the coordinate here is 1.0. When the load is here, the reaction here is 0.5. And when the load is here, the reaction here is 0. Okay. And similarly, if you draw this for the B sub y, you do what? You just keep this one as the pin support. This is going to be the pin. And you release this and then you put this B sub y and you move this one for let's see, we put it in this color for 1.0. Okay, and the shape of this is going to be the inference line of b sub y, and then you use this when the force is at A. Okay, the b sub y here is 0. When the force move to the middle, the b sub y is going to be 0.5. When the force is here, the b sub y is 0. So from this one, you see the inference line indicate the value of the reaction A sub y when the force just move along the length of the beam, or the inference line of B sub y indicate the coordinate or the magnitude of B sub y when the 1.0 unit load move along here. So next, when we change this beam into the statically indeterminate, for example, let me use this one. Okay, and this one has the pin as before as A, and the roller as B. However, I increase the support at C here. So this beam going to have the degree of indeterminacy of what? This is going to have the A sub y, right? This is going to have the A sub y, has the A sub x, has the C sub y, has the B sub y. The unknown is going to be 4. We have 3 equations of equilibrium. The degree of indeterminacy is equal to 1. However, even though you change the beam into the statically indeterminate, the Musler-based law is still applicable. What it means is what? You just what? If you have the beam like this, I'm not sure you see it or not, and you just fix the C and the B, and then you just change this one. Okay, you just release the resistance of A sub y, and then you let the A sub y push this one into the 1.0 unit, and then this is fixed, this is fixed. The beam will deflect like this. The same thing. If you have the beam like this, okay. I'm not sure how come is you your time. It's supposed to be me, right? To share this one. Okay, you can see me, right? And then when this occurs, you see the shape of this inference line is like this. And then I will draw the inference line of B sub y again. This one. I will release the resistance to the B sub y, and then I use the B sub y, push it up. The shape over here is going to be the inference line of B sub y. I will draw to you later. And then if you like to draw the inference line of C sub y, you just release the ability to resist of C sub y, and then you push it up for 1 unit. You get this shape to be the inference line of C sub y. So by doing this, let me draw the inference line diagram of the B sub y. Now, let me just draw this, sorry. Just use this beam again. Now, this time, inference line of B sub y, A still pin, C still roller. You just release the B sub y out, and then you push this one up by apply the force B sub y. This one will move for 1.0 unit. And then the shape of the beam is going to be the inference line of B sub y. The same thing also occur when you draw the inference line of C sub y. So this A is going to pin, B still roller, and then you use the C sub y, push this one up for 1.0 unit, and then this shape is going to be the inference line of C sub y. Okay, see now. So what is going to be the equation of this inference line? I will talk about this later. Inference line of A sub y will determine from the deflection at point X when the force applied at A divided by the deflection at point A due to the force at A. Okay, and then you also can find the inference line of B sub y is going to be the deflection. Is the shape of this deflection of any point X. Okay, is depend on the position of this X, this point X of X. When the force applied at B, and then is going to divide it by F sub BB. Okay, and you can see if the point X is B here, it's going to be F sub BB divided by F sub BB. So this is going to be 1.0. And then if you change X into A, it's going to be F sub AA divided by F sub A. It's going to be 1.0 also. Okay, I will talking about this later. And then if you like to find the inference line of C sub y, again, you will see it's going to be the ratio of the deflection divided by the deflection F. The deflection F is the deflection due to the C sub y. Deflection S point X due to the force applied at C. And then divided by F sub CC again at this point C. Okay, if this change to F sub C, it's going to be F sub CC divided by F sub CC, then it's going to be 1.0. Okay, and then the second one, you understand to draw the inference line diagram. You understand the equation, and then later you should be able to determine the loading pattern from the inference line diagram that produce the maximum reaction. Okay. Talking about the loading pattern, you have the dead load, okay, uniformly distributed dead load. You have uniformly distributed live load, and you also the live load that is going to be the point load or concentrated load. By doing this, you see the inference line of the positive going to be large. If we consider the pattern of the dead load, if only the dead load is this one, I should like this one to be the live load. Okay, the dead load always distributed across the beam. So don't worry. Anytime you talking about this dead load, distributed dead load is some kind of self weight, okay, of the beam. So it's still there. But the live load, uniformly distributed live load, can be placed to the position that produce the maximum of what? Of A sub y. Since the inference here is large, so you got to put the loading pattern like this. So how about the B sub y? Coming to the B sub y, the inference line is different for the A sub y. Okay, this is going to be the same beam. If we're talking about the dead load, so the dead load always at the full span. But this time, this is going to have the larger inference compared to the negative. You can push the ruler, and you can see the one that's pushed on this side is going to be larger than the negative. Okay, so in this way, the uniformly distributed live load in this way is supposed to put into the position here. See, they are different. And then the last one, if you would like to provide the maximum C sub y, what is going to be the loading pattern This way, you see, all are positive. So in this way, you just put this is the uniformly distributed dead load. But for the uniformly distributed live load, it's going to be like this. So you can see the loading pattern for the A sub y maximum A sub y, for the maximum B sub y, for the maximum C sub y, they are different. Okay, and then what you can use is going to produce the maximum reaction. You can use that reaction to design the support, to design the foundation. And then if you have the live load, that is going to be the concentrated load or point load. In this way, you got to determine the maximum coordinate of the inference line. For this one, the maximum is here, so the P in this way is supposed to be here. And for this one, the P must be here. And for this one, the P must be here. That's what we had previously in the inference line diagram of statically determinate beam. Okay, from the theory of structure. And then you can apply this concept to the statically indeterminate beam. So there is nothing new. There are 3 homework for you guys to turn into me 7 days after I finish this chapter. Okay, and it is in my book. I post my book. It is in Thai book anyway. Sorry for that. I supposed to change it to English. Anyway, you guys please using this book first. Anyway, I will change the problem later. So what is the inference line? Okay, is in short is just the diagram that show the changing in the, for example, reaction at a given point. Okay, when the beam is acted or subjected to by the moving 1.0 moving load along its length. Okay, sometimes, for example, for the crane over here, we didn't care about the reaction, but if we prefer to design the wielding point at this one, for this one, you got to determine the M max, you got to determine the V max. And since this one is statically determinate, just go back and take a review of this one. If you like to draw the inference line of this beam, okay, this beam of what? Of V sub A. What you do is you use the Musler-based rule. Just release the V sub A. Okay, by doing that, we got to put the roller guide. Okay, roller guide over here. We got to put the roller guide, and then you put the positive shear. Okay, so go back. What is going to be the positive shear? If you cut the section over here, following the sign convention that we studied previously in the static, in the mechanics of material, in the theory of structure, this is going to be positive shear on the left hand side, and this is positive shear on the right hand side. So by doing this, this is going to be the pin. Pin is the rotating point. So what you get is the beam going to change the shape like this. For this one, it's going to move up, change the shape like this. And I should note that even though you release the V, okay, we still have the M over here. So it's moved like this with the M still here. And what is the requirement of this? The slope here is going to be in parallel, and also the summation of the deflection here is going to be 1.0. Okay, and then again, if you go back and let's say The length from here to here is A. The length from here to here is B. And the total length of the beam is going to be L. You can compute this one going to be minus A over L. This is positive B over L. You can use this. There are a lot of this kind of structure that you're going to use your own knowledge. I just want to review it. If you're going to design this crane, you got to do what I did here. And then if you prefer to find the Mmax, what you're going to do is you're going to draw the inference line of the moment at point A. So the support here and here is going to be the same. You need to change this one into the hinge to release the M sub positive M here. Okay, and then you apply the moment to this point. When you apply the moment to this point gonna move up to here. And since this one is the rotating point, you get the shape. This is going to be the inference line of M sub A. On the top, you get the inference line of V sub A. Used to determine the Vmax. This one is used to determine the Mmax. And if you recall it, the coordinate here is going to be AB over L. The requirement is here is going to be the angle here going to be 1.0. So you got to put the 50 kilonewton according to this. If this one is 10 meter, this is 4 meter, this is 6 meter. So the coordinate here is going to be 0.6. The coordinate here is going to be minus 0.4. So this is going to produce the maximum effect. Okay, by doing this to produce the maximum shear basis on the inference line diagram, you got to put the 50 kilonewton force over here. Okay, to produce the maximum effect for the shear here. And then you determine the Vmax basis upon this. This is going to be 4 meter. This is going to be 6 meter. Again, basis upon this one, you also can put what? Put the 50 kilonewton. Since the coordinate max is here, so this 50 kilonewton supposed to be here. By putting the 50 kilonewton at point A, okay, you produce both Mmax and Vmax. This is the example for using the inference line diagram basis on the knowledge that we learned from the theory of structure. That's going to be this kind of crane. Okay, you can find this crane at our F4 building. This crane is going to be statically determinate beam. Okay, the transverse beam of the crane can be assumed that, and we discussed this already. However, if you taking a look at this beam, this longitudinal beam, they are two of them. They are the statically indefinite with 2 degrees of indeterminacy. Why? You can assume this is pin, this is roller, this is roller, and this is roller. So degree of indeterminacy will be 2, 3, 4, and 5, and minus 3 equation of equilibrium. You got this going to be the statically indeterminate beam with 2 degrees of indeterminacy. And again, the beam, the red beam, can move along this. When it's moved, okay, it's moved position, we're going to consider the inference line of this statically indeterminate beam. This is an example of the crane in our university. You can take a look at F4 building. Okay, if you stay very close to the university, just come and take a look at it. To consider another example, consider the beam of the bridge. This is going to be a kind of precast pre-stasis, okay, concrete beam. We use a lot in Thailand to build the bridge, okay, the precast pre-state concrete beam. There are many of them across this one. Okay, during you build the foundation, okay, you put the cap, the pie over here, cast the pie cap of this going to call the pie cap, okay, and under it is going to be the pies, and then you cast the pier. You cast the pier. This is going to be the pier of the bridge. This is P-I-E-R. After you cast the pier, finally you cast the cross beam. This is going to be the cross beam. Okay, this is going to be the cross beam, and then before finish casting the cross beam, you chip the precast pre-state concrete beam to this side by putting into the 18 welder or 24 welder and use the crane to lift it and put it over here. So this one can assume to be a kind of statically determinate beam. Okay, and why the pick up moving along this bridge, okay, you're gonna imagine the load also gonna move. So this one, the vehicle load gonna move along the beam, and you got to use the concept of inference line to again determine the M max, determine the V max. If you go back to the theory of structure, you may recall about absolute maximum shear. Okay, also the absolute maximum moment. Do you remember that? If not, go back to review it. Okay, we have this knowledge to be used to the analyze of this kind of beam if you work for the Department of Highway in Thailand. Another example, this one I took this one for from the California. Okay, when I visit here, there is a joint here. Okay, between the structure. Again, you can see this is the vehicle. This is the vehicle. In the design of connection between the precast pre-state concrete beam, this portion of the beam, okay, and this portion of the beam with the cross beam, okay, for this elevated highway, you an engineer, you must let the vehicle load move along the beam again, and then use the concept of inference line diagram to determine the shear force, okay, and if this is fixed, you're going to determine the maximum moment that occur here. Again, how? Okay, you guys supposed to go back and take a look, because this kind of beam can be assumed as statically determinate. Okay, now let us review what we have seen the engineering static. We have the shear and moment diagram. When you know the shear and moment diagram, see the engineering static, you just point load here. For example, 10 kilonewton. And then let's say this is going to be 1 meter. This is going to be 3 meters. Can you go back and draw the shear diagram and moment diagram of this beam? Sure. Okay. You just check what is going to be the reaction here. You draw the free body diagram, and then you use the equation of equilibrium. You can determine the reaction. And then when you draw the shear and moment diagram, you can use the graphical method. Okay, graphical method to draw it. You have what? You have the dv by dx equal to minus w. You have v sub b minus v sub a equal to the area, okay, of W between A to B. Okay, and if the force is downward, delta V is negative. If the force is upward, delta V is positive. So by using that, you draw this shear diagram. Okay, and also there is another set of equation. For example, dm by dx equal to v, m sub b minus m sub a equal to, sorry, this is going to be negative, or the area of v diagram between A to B. And if you have the moment counterclockwise, the delta m is going to be negative. If you have the m in the clockwise direction, the delta m is positive. So you can draw this moment diagram, and then you get the V max, you get the m max. You use this V max, M max to design the beam in accordance with the design code. Okay, this is the shear moment diagram that we have. In this way, again, the load that we consider is the fixed load. This fixed load can estimate from the dead load and live load. Okay, that's going to follow the building code. And when you just studying static, Ajahn give this to you in the theory of structure also. But when you study the steel design, reinforced concrete design, you got to determine the dead load and live load from this building code. And then you use the way you study for the engineering static, for the theory of structure, to draw the shear diagram and moment diagram. Okay? I don't know you record it or not, but if you won't record it, go back and review it. You still use this one in the steel design, in the reinforced concrete design. And then go next to review the inference line. If you like to draw the inference line, Maxwell, Basler, okay, give us the principle that help us to draw the diagram. I did draw for you, and this is the word that we use. The principle is so easy. If you like to draw the inference line diagram of R sub A, what you have is you just release the resistance this is pin, to A out, take the resistance out. So the B release still the same. Since this is roller, so you just put the A sub Y, let it move for 1.0 unit. That is going to be the inference line of what? Of A sub Y. Okay. If you like to draw the inference line at point C, again, by using Maxwell, Basler, let me erase this, use the red one. You release the resistance to the V sub Y. This one gonna be pin, this one gonna be roller. By releasing that, you just put the roller guide at the point C, and then what, you put the positive shear on the left and on the right, and then again this one gonna move like this. You got what? You got the inference line of shear diagram, and there are some requirements. You need to go back and take a look from the first slide. Take a look of it. What is going to be back? This is going to be 1.0. This is going to be in parallel. Okay, and again, let's follow the word here. I will not read this word. Okay, if you prefer, you go back and read it. But for me, I prefer to draw the picture and explaining to you guys. When you like to draw the inference line of the moment, you just take the resistance to the function out. Just take this one out by putting the pin. So this is no, sorry, this is hinge. Okay, this is hinge. This is going to be the roller guide. Okay, this is roller guide. This is going to be the hinge. And then you apply the positive moment act into this. This one gonna move to a new position here. And then the shape of the beam is going to be the inference line diagram of M sub C. Okay. Okay. Practice this. Don't do the remember of this thing. You will forget it. You will forget it really easy. But if you do this thing, it's going to last long. The memory going to be last long. Okay. The detail of this, you just go to Kit. I did explain to you guys already. Okay. This is for the inference line for the reaction at A sub y. Okay. For this one, you just change this one to the roller guide. And then put the positive shear into this beam. And this is the rotating point. The shape of this one is going to be something like this. And again, if this one is 5 meters, this is 5 meters, this is 5 meters, you can have this one for 5/10. That is going to be minus 0.5. Over here, you're going to get this one for positive 0.5. Okay, and coordinate of this inference line diagram of statically determinate can determine from similar triangle. If this one 5 meters and this one 5 meters and this one 0.5, this one gonna be positive 0.5. You can determine the coordinate of this inference line easily. And you also don't forget about the requirement of this inference line diagram. Okay? And move to the inference line of bending moment M sub C. You got to put the hinge at point C. When you put the hinge at point C, you apply the moment over here. Point C will move up to the new position. If this one is 5 meters, this one is 5 meters, this one 5 meters, this one 5 meters, this one gonna be AB over L. This one gonna be 10 meters for the L. It's gonna be 5 times 5 divided by 10. That is gonna be 2.5. Okay, this is the rotating point. The beam move, you get this shape. If this one is 2.5, this one gonna be minus 2.5, and this one also minus 2.5. It's very simple. And don't forget to follow the rule. This is gonna be AB over L, and the relative angle here gonna be 1.0. Okay, and this 1.0 also will use when we do the inference line diagram for the statically indeterminate. Okay, okay, move back to use of the inference line diagram of the simple beam. Okay, after you can do the inference line diagram for the theory of structure, for example, this is the inference line diagram of the point of C. Okay, when you do this one, you put the roller guide here, and then you put the positive shear, this one downward, this one upward. Okay, this one is going to be minus A over L. Since the A is 2.5, it's going to be minus 2.5 divided by 10. And then this one will be minus 0.25, actually. For the top part of this is going to be positive B over L. So this is going to be 7.5 meter. This is going to be positive 7.5 divided by 10. This is going to be 0.75. And you can see the area of the inference line on this portion is larger than on the negative portion. Now we have the life load. This is the concentrated life load. This is going to put at the maximum coordinate. Okay, you got to put this for the maximum coordinate. And also you have this one. This one is what? This one is uniformly distributed load that can be arranged with appropriate length. Okay, This is going to put what at the maximum area of inference line. This is going to put as maximum coordinate of inference line. So by doing this, the 4 kilonewton, going to put to which position? Okay, which one? To get this one, the maximum coordinate is here. So for sure, the 4 kilonewton must be here. Okay, must be here. And then the uniformly distributed likewise basis on this maximum area. So you got to put this in this portion. Now, how can you determine, okay, the maximum V sub C from this loading pattern? You got to times 4 kilonewton by the coordinate here. And you got 2 times the uniformly distributed load by the area here. It's very simple. The area of inference line of statically determinate on the simple beam is triangle. So the calculation is easy. Okay, the area can be computed easily. But since the inference line of statically indeterminate is curved, okay, you got to go back and review the what's so called the integration or integration of a function, okay, to find area. Okay, this is your guess. Just go back. You got to find the area for a curve. Okay, and then by doing this thing out very simple, you get the shear here going to be 8.625. The shear that's occur over here. And then from the shear that you have over here, you can draw the free body diagram. Okay. The shear is going to be positive, so it's going to be 8.625. Okay, if you cut it on the left hand side, and then what you have is you can use this shear to determine the A sub y, the A sub x, and the B sub y, and the moment over here. Can you do it? That is going to be M sub C for this loading pattern. Okay, this is going to be your assignment. Just go back and review it. Okay, you can find the A sub X, A sub Y, and M sub C easily by using the engineering static. Okay, then this is the loading pattern that produces the maximum shear force at C. But if you prefer to find the bending moment at C, the loading pattern is going to be the same? No, because the inference line diagram of the moment can be done like this. Okay, you just put the hinge into the C. And this is going to be the pin. This is going to be the roller. When you put the hinge here, you put the positive moment and move this one up for AB over L. And then you get this one as the inference line of M sub C. By the inference M sub C, you can see all the area positive. And the maximum is going to be here. So the 4 kilonewton going to be at the same point as before. But the uniformly distributed load going to be like this. Okay, you can see the loading pattern just different depending on you determine the shear at C or determine the moment at C. And then you can determine this one and maximum moment due to this kind of loading pattern. And then you can use this M sub C and V sub C to design the beam. This beam may be the crane. the crane at the F4 building, as I just mentioned before. Okay, and 4.2, from the introduction, we need to have some more knowledge in order to determine the equation of influence line. Okay, we got to use the Maxwell reciprocal theorem. By the Maxwell reciprocal theorem, there are words here, but I don't like to put the word. Just consider the beam. Okay, when the beam is subjected to a point load at point A. Okay, and you can find the deflection at point B by using the what's so called, for example, the conjugate beam method, or you may use the unit load method to determine the deflection. Whenever the structure subjected to 1.0, we use the F as the deflection, the symbol F as the deflection. This is going to be the deflection at point B. Okay, due to the force at point A, this is going to be the deflection. Okay, the vertical deflection at A. Okay, due to the 1.0 load at B. Okay, and then again, you just change things. Just put the 1.0 unit load at B, and then you determine the vertical deflection at what? This is going to be the vertical deflection at A due to the loading at B. Oh, sorry. This is the first one. Going to be the vertical deflection at B due to the applied load at A. Okay, it's going to be equal to the vertical deflection at this one, at A, due to the applied load at B. Okay, and you will have this kind of word, and you can prove it. Just run the program computer. You're going to determine the deflection at point B due to the unit force at A. That is going to be minus 16.01 millimeter. And then you do again. You're going to determine the deflection at point A due to the force, unit force at B. And these two, they are equal. See? Proof. Okay? And then go to another problem. This time we're talking about the slope. We're talking about the moment. This one going to be slope at what? At B due to M equal to 1.0 at A. Okay, and then you do it again. This is going to be equal to what? Equal to the slope at this one, as A. Okay, and due to the 1.0 unit moment at B. Okay, and they are equal. Putting the word like this. Prove it. Okay, this one subjected to the moment at A. So over here we are looking for the slope. Okay, the slope at B, due to the moment. Okay, at A. Okay, what we have is going to determine the slope. It's going to be here. And then you apply the moment to the beam and consider the slope here, this is going to be theta at point A due to the moment at B. Okay, again, you get this. And then you can see this one and this one, they are equal. So proof. And the Maxwell reciprocal theorem also consider for this case, for the slope and vertical deflection. They said if the 1 point unit load applied A, the slope at point B due to the force Fa, okay, is going to be equal to the vertical deflection at point A due to the moment at B. Okay, again, you put this one in the word like this, and you can prove it. The deflection here is going to be this value. Okay, and then you put the moment over here, 10 by the 10. This is 10 equal force and equal moment. You get what? You get the deflection over here. It's going to be this value, and they are equal. Okay, all proof. That is the new knowledge that's required for us to determine the equation for the inference line for the statically indeterminate beam. Now, we move a little bit further. Review about the consistent deformation. Okay, we know this in the theory of structure, the last chapter, okay, of structure. And you consider this beam, this beam has what? This beam has 4 unknown, A sub y, A sub x, and the moment here of M sub A. This is fixed support, okay? And you have this one also, this is the roller. So this is fixed, something like this. This is the roller. And when you push it, this is the deflection, see, of this beam. And this is fixed, that has 3 unknown. So the degree of indeterminacy of this beam is going to be 4 minus 1 equal to 1. And most of the time we got to set up the redundant. Okay, if we set up the B sub y as the redundant, we may use the principle of superposition. Separate this beam. The first beam is subjected to the applied force P. We call this one is the primary beam. Okay. Oh, sorry, this is not yet. This is just the same as above. Sorry. Just take this one out. Erase this one. And we can separate this one into the first one. This is primary beam. Okay. And then another one. This is the beam that is subjected to the redundant. So the first one is for the P. The second one for the B sub y. For the first P, the beam defect at B of delta sub B. Okay, and this is delta sub B. And the B sub y move this one for delta prime sub BB. Since B sub y is unknown, usually we find F sub BB, the deflection at B due to B sub y equal to 1 point. Okay, the deflection at B due to the force 1.0 at B. And since B sub y set to be 1, if B sub y change to any value, just time the B sub y with the F sub BB. And now we can see that this one and this one has 0 deflection. Okay. And this one have delta sub B, this one have B sub y, F sub BB. If you put downward is positive, this is going to be 0. This is downward is positive, and this is upward going to be negative. And then you rearrange it, you can determine the redundant force. This problem is the problem requires your guy to use the knowledge of deflection. Okay, from theory of structure, there are many ways to calculate it. But if you cannot compute the deflection correctly, you will get a bad grade for this chapter. So go back and review the whole thing, okay, to connect everything together. So now we are ready to determine the inference line equation. So just consider this again. This beam also have degree of indeterminate C equal to 1. Okay. Now, when you have a beam, you just set up the 1.0 unit at any point D that may have the coordinate of x from the point A. And since this one is going to be the statically indeterminate with degree of freedom equal to 1, you got to set the reaction at point A to be the redundant. Okay, must make it as the redundant. If you push this one as the redundant, again from the previous one, you may take the roller out and put the A sub y like this. Okay, this is going to be the redundant, and then you can use the A sub y as the redundant, and you can draw the picture. This one will equal to, okay, you just take this one out and put the A sub y. So just put the A sub y over here. Okay, so the top picture gonna be equal to the middle one plus the bottom one. Okay, and then what we have again from the separate two cases that we mentioned, we just consider the deflection at point A, and then we can write the compatibility condition at point A. This is 0. This is the deflection at point A due to the force applied at point D. This is positive. Okay, and also this one gonna be the deflection of A sub y times F sub AA, the deflection at point A due to the unit point load at A. Okay, so you can time A sub y, and it is moving up the same as this one. So this one is positive. You rearrange it, you get it. And now go back to the Maxwell reciprocal theorem. This is negative, is no good. Just consider this one. Okay, under the force of A sub y equal to 1, you get the deflection over here as F sub the deflection at D due to the application force at A, and it is downward, and it is going to equal to F sub AD. Okay, so by doing this, you just change this one. Okay, minus F sub AD equal to positive F sub DA. So you get the equation to determine the inference line of A sub y. Okay, in this equation. Now, if you consider this equation, this is the equation from the deflection at point D when the force applied at A divided by the deflection at A when the force applied at A. Okay, in the positive thing, the force can be any position. Actually, the D can change to the position of X. What the meaning of X? If this is going to be 1.0, this is the deflection at point A due to the force at point A. This is going to be the deflection at point 1 due to the force SA. This is going to be the deflection at point 2 due to force SA. This is going to be the deflection at point T due to the force SA. This is the deflection at point D due to the force A. This is the deflection at point 4 due to the force S. Okay. Based on this, if you like to draw the inference line of A sub y, take the resistance of A sub y out, and then apply the A sub y equal to 1 unit to the beam and determine the deflection. When you determine the deflection, you put all the deflection into this one. You get the coordinate of the inference line. Okay, so the first step, if you like to determine the coordinate of the inference line of A sub y, take the resistance to the A sub y out and put the force A sub y equal to 1. And then you determine the deflection. To determine this kind of deflection, you got to use many kind of methods such as conjugate beam, such as the unit load to determine it. Okay, and if you determine all the deflection in the form of equation, you're going to get the equation for the coordinate of the inference line of A sub y, and then you just put them into the equation. Okay, inference line of A sub y equal to the deflection at point X. Okay, when the force applied at A divided by deflection at point A due to the force applied at A. And then if you consider this one going to be F sub AA divided by F sub A. This one is 1.0. And the other, you can determine the coordinate of this. Okay? And if you not determine the deflection individually, if you determine it in the form of equation, you will get the equation of the inference line of A sub y. I will demonstrate this for the next lecture. Okay? Okay. This one is equation that I just mentioned. Okay? And just change the x. Okay, just change the x. Everything can determine like this. And this is the word. Okay, let's explain the picture below, picture above, all of them. Okay, if you understand it, you have the YouTube, and then just trying to understand what is said here. It's not that hard. You guys are good. Okay, you can review it. So go back, review the chapter of deflection in the theory of structure. Next, go to the inference line equation for the shear force at E. Again, following the previous discussion, we're going to release the resistance to the shear force at E. From this one, we apply again the 1.0 unit load at any given point D. And then we use the V sub E as the redundant. When we use the V sub E as redundant, we got to release the resistance to V sub E out. Okay. When we release the resistance to V sub E out, this one going to produce some deflection. Okay. And then when you put the V sub E into this structure for 1.0 unit, you get an answer. So what we have is the relative deflection at E is going to be 0. Okay, and this one is going to be the deflection at point E due to the force at point D. Okay, and this is going to be the deflection at point E due to the force applied at point E. Okay, and then this one will be this one plus this one. Now, you consider the point the point E, and then you can draw the compatibility condition at point E. 0 is here, okay, and then f sub ed and f sub ee, they are in the same direction, so just put them as the positive. So v sub e going to be like this, and again this is not convenient to do so, and come back into this picture. You can see f sub de over here will be equal to f sub ed, but with the negative. So put the negative here. This is going to be positive. Just take this one into this portion, and then you get the equation to determine the shear force at point. And now, as before, you got to do what? You got to first, if you like to draw the inference line of V sub E, first one, you got to remove, actually it's supposed to be remove the resistance to V sub E, okay, out of the beam. Okay, by doing that, we do by put the roller guide. Okay, you put the roller guide at E. Okay, and then the second, let V sub E equal to positive 1.0 apply to the beam. Okay, when it's applied to the beam, what we have, the deflected shape. The deflected shape is the inference line of V sub E. Okay, and the coordinate of inference line of V sub E is this one. That means what? You got to check this one to be the x. You got to determine the deflection of this one. Okay, and then if you follow this, you got to find the deflection first. You got to find the deflection f sub x e, and second, you find the deflection f sub e, and then put into this equation. You can determine the coordinate of this inference line at point E easily. Okay, and this is the real shape of inference line basis on the experiment. Okay, we have what? We have this one and the support, this one and the support, this one support, this one and support, and then you put the roller guide here, and then you put the force downward here and put the force up. So you get this shape as the inference line of V. For example, if this one is E, V sub E. Next, inference line for the moment at point E. Again, the beam is statically indeterminate with 1 degree of indeterminacy. You put the loading at point D. Okay, and then what? You use the moment M sub E as the redundant. You got to change the point E into the hinge under the 1.0 unit load. The hinge at E move to E palm and has the slope, the slope alpha at point E due to the force at D. Okay, the slope at point E due to the force at D. And then the next one, you got to plus this one with the moment of what? Of m sub e equal to 1.0 unit. Okay. And then you get the deflection at point E to be alpha sub E. Okay. And the deflection at point D, the deflection at point D due to the force at E. This is the deflection at point D due to the force at D. But we're going to consider only point E, the relative slope of the beam from this one is going to be 0. Okay. And since the rotation alpha sub ED and alpha sub EE, they are the same. Let them are positive. So M sub E gonna be like this. And then we have Maxwell reciprocal theorem. Now, alpha sub ED, which is not inconvenient to use it. We just change this one to positive F sub DE and put it over here. You got equation here. And again, the explanation still will be the same. First, if you like to draw the inference line of M sub E, release this one and put the M sub E equal to 1.0 unit load. And the shape of the beam is going to be, the deflected shape of the beam is going to be the inference line of M sub E. Okay. And the coordinate of the inference line of M sub E can be determined from this equation. And then you got to change the point D into any point. So just change this one to H and you can write this general wording to be in this form. Okay. Okay, and from the experiment, if you like to draw the inference line of this, just remove the resistance to the moment at point E. And then apply the force. Okay, move this one until you get this one of 1.0. This is going to be the shape of the inference line of M sub E. Okay, but from this one, don't forget also this one, this one relative, this one gonna be 1.0. And then if you draw the tangent line here, the requirement gonna be in parallel. This is important. Okay, and then it's follow the Muller-Basel law principle, even though the beam is statically determinate. Okay, just move it further. Let us compare the inference line of statically indeterminate with the statically determinate beam. This beam is statically determinate. It has 1, 2, 3, 4. So the degree of indeterminacy equal to 4. And then you're gonna minus it with the 3 equation. And since this one is in, we have another special condition because the moment at E is 0. So the degree of indeterminacy here is 0. Now, you use the Muller-Basel principle again. Just release this one. Just release just take one. This one. Just take this one. Change this one into the roller in this direction. And then you apply the AR sub A. Okay. Move this one for 1.0 unit. And this one rotating point. This one the hit. You got the shape of statically determinate as the straight line. Okay. And the shear also. And the moment at E also. So review your own knowledge. For the new one, we will draw the picture of this beam statically indeterminate beam. The example that we have is more complex than this. Okay, I can show you the first one very easy. Inference line of AR sub A. Release this one out and then push this one up for 1 unit. This one is the shape of the inference line of R sub A. How about inference line of R sub C? Just take the C out, push this one up. This is the shape of inference line of R sub C. And inference line of this beam, or if you're interested in the point B, just take the resistance to the B sub Y out, move it for 1 unit. This is the shape of inference line of B sub Y. Okay? For the shear at the moment, it's very harder to show. But the basic from this is going to help you to understand things. There is the example here. And I like to show you by my drawing. Just let us move to, okay, this one. Okay, just let us move to this one. There is some question on the top of this extra example. I like you guys to go back and trying to answer it. All of the answer for these 2 problems can be determined from the lecture note or from the textbook. Okay, so let's move to this. Let me do some zooming. Okay, first we like to determine the inference line of R sub A. Okay, first we have the equation inference line of R sub A is equal to the ratio of what? Of the deflection at point X. Okay, due to the force at A. Deflection is come from the deflection. That's mean we're going to draw the deflected curve divided by the deflection at point A due to the force as A. So by doing this, this is going to be the same, and the same. This one is pin. Just change it into this kind of roller. Since you got to release the resistance of what? Of A sub Y. Okay, and then you got to put A sub Y to move the beam. Okay, to move the beam, to make the beam deflected. So this one gonna move for 1 unit. Let's put this one for 1 unit. Let's say this is going to be 1 unit. Okay, and then this one would move. So the rest of this one gonna have some kind of deflection, and they're gonna deflect in accordance to each other and get smaller and smaller when they are far away from the applied force here. Okay, and you can see this is going to be positive, this is going to be positive, and this is going to be positive. The rest of this negative, this is negative, and this is negative. There is the positive and negative coordinate on this. So it is imperative, it is a must for you guys to go back review the ways to the methods to determine the deflection. Okay, next let us move to the point E. The point E is here. Okay, the point here, the same except at the point E. You got to release the resistance to R sub E. Before this is R sub A, R sub E. And then you put this R sub E. Okay, before this you put R sub A. to move this one for 1 unit. Okay, just move this one for 1 unit. When this one move, this can rotate. So this portion of the beam will deflect like this, and the other will follow the elastic curve that we studied before from the theory of structure. Okay, and then again, this has the positive, negative, negative, positive, and negative. The area in this one will govern the other area. The same thing as this one. Okay, this one going to be large compared to the other. Then the inference line of R sub E is equal to the deflection at point X, any point X, due to the force applied at B, divided by the deflection at point B due to the force at B. So that's why this is going to be 1.0 unit, because it's going to be F sub BB divided by F sub BB. For example, this one is going to be F sub AA divided by F sub AA also. This one going to be F sub BB divided by F sub BB. Okay, following the Boosler-Basler principle. Now, we move to draw the M sub C. Okay, so what is the C? The C is here. Okay, and all the support. Okay, it's gonna follow the same thing, but you got to release the resistance to the moment at C. That means you got to put the hinge over here, and then you got to apply the moment M sub C. When you put M sub C, this is the hinge. This is going to have some deformation like this. Okay, and then it's going to follow everything like this. On this side, due to this moment, on this side, it's going to deflect by this moment and have the shape like this. Now, this is going to be negative. Negative of this is going to be, okay, and this is negative. The other portion going to be positive. Okay, now this is going to be the inference line of M sub C. If you can recall, the inference line of moment going to be the deflection, and then divided by the slope. This is the deflection at point X due to the moment applied at C. And then this is going to be alpha sub CC. And don't forget the requirement of this, the relative angle that is going to be here, going to be 1.0. Okay, the same as this is 1.0. This is 1.0. This is relative angle is 1.0. Now we move a little bit further to the left hand side of point C. Okay, that means the inference line of V sub C L. This is going to be at the C on the left. Okay, you just release the resistance of V sub C L. You got to put the roller guide. When you put the roller guide, what we have is we got to then put the V sub C L into this portion. So on the left is going to be downward, on the right is going to be upward. Okay, and what we have on the right, there is the roller that's stick into it. You can see here the force shear CL here cannot move this one up because the roller here stick it. Okay, so the later portion here, okay, can be moved, and the movement here is going to be 1.0. And since when you cut any section, what we have, when you cut it, there is the shear, okay? Also, the moment, when you release only the shear here, there's still the moment here. So there is the moment resistance here a little bit. So the movement here gonna be something like this, and there is the slope here, okay? And this one cannot lift up, it's still here, but with the same slope, okay? Here. So this one will deflect like this. Okay, that is going to be the inference line of V sub C L, which is going to be the deflection at point X when the shear applied at C on the left divided by the deflection at point C on the left when the shear applied at C on the left. That is the equation of this. Now we move to the right, okay, of point C. So we just draw the same beam as before. Now what we have is going to put the roller guide on the C on the right, and then put the force downward here, upward here. What happened is, again, this one cannot move, this one can move, right? It's going to move for 1 unit, and then the deflection of this beam going to be like this, and over here to here is 1.0 as before. And the requirement here is going to be the slope here and the slope here. They're going to be in parallel. So this one gonna have the shape over here like this. Okay, it's going to be curve, very smooth curve. Okay, and the inference line of V sub CR is going to be the deflection divided by the deflection. Okay, and then what we have here is going to be deflection at point X due to the the shear at point C on the right, deflection at C on the right, and then due to the shear force at C on the right. Okay, it's not that hard, but it requires you guys to do some practice, and then M sub H is over here. Okay, and by doing that, all these are going to be the same. And then at point H, what occurred at point H? Moment. You're going to inference line of M sub H is going to be F divided by slope. So you put what? You put the hinge and then put the moment M sub H into the hinge. And this one going to move. How many it move? Not AB over L. You're going to compute the deflection of this. But by doing this, what we have, the deflection is going to have the shape something like this. Okay, and the angle here required to be as before 1.0, and this one is going to be the deflection as any point X when the force applied at H. Okay, and the angle here alpha sub HH. Okay, next. It's very fun to do so. V sub H. There we're going to do the same thing. Okay, at H, the support, all of them, this is pin. Okay, and just put this one, the roller. You got to put the roller guide here and put the force here of V sub H. This is M sub H. Okay, and downward and upward. For that one is going to have this shape. For this one is going to have this shape. Is required you guys to do some practice to get this. And the most important over here, you're going to get this one in parallel. and the summation of this is going to be 1.0, and then inference line of V sub H equal to the deflection at point X due to the force at H, and then divided by F sub HH. Okay, that is the first thing. You must be able to draw the inference line diagram. And then the next one, if we have uniformly distributed live load, sorry, supposed to be live load, okay, for what? For R sub E. How should we put the uniformly distributed load on the beam to obtain the highest reaction at point E? Okay, go to the point E. Go to the point E. Okay, is inference line of R sub E. And then you see the effect of positive and positive is large. So for this one, okay, you got to put the uniformly distributed here. This is negative, this is negative, and this is positive. So we got this one as the uniformly distributed that's produce the maximum R sub E. Okay, and then for the M sub C. Next, we come M sub C. M sub C has the negative, and then the negative is going to be 2 of here and 1 here. You get this is the pattern, the loading pattern that's going to produce the maximum M sub C by putting this. Okay, you can get the result of this. And then the last one, M sub H. Okay, M sub H is here. That is positive. Okay, this is positive. This is positive. To following this is going to be this one, positive, and this one. Okay, you get the loading pattern, and you can see all of the loading pattern that we get here, they are not the same, they are different. So when we let the load can put in the way that can produce the maximum effect, the analysis will get the correct absolute maximum for the reaction, for the shear, and for the moment. Okay, this is the example. And again, the use of this, the American concrete institute use the concept of inference line diagram to produce the coefficient uses to design the reinforced concrete beam. Okay, I let you guys to go back and take a look at this thing. Okay, I show you guys already. Okay, here the American Concrete Institute. Okay, use the concept of inference line diagram to consider the loading pattern. The same one, they use the different loading pattern for the continuous beam as I show you to produce the maximum shear force, to produce the maximum moment in the beam. And then they use this one to develop the moment coefficient and the shear coefficient that can be used in the design of the reinforced concrete beam based on the ACI design. Okay, this is inference line of inference line of M sub B. They just put this hinge and put this moment M sub E, move this point into here, so you have the deflected curve of this one to be like this. And then this is the positive, this is the positive, this is the positive. So the loading pattern to produce the the positive moment. This is positive moment. Okay, gonna be like this. Positive moment occur at the mid span of the beam. This one going to produce the maximum negative moment that's occur at the column, at the support. So by doing this, just put the hinge here and put the M sub C here, you get the deflected curve show here. And then the negative control the inference line diagram. So this is another loading pattern that's produce the negative moment. This could do the positive moment at the first span. And the shear also on the left. Also, sorry, on the right. Okay. And following this, they consider the frame. Okay, the T-span frame, and the requirement, the span of the frame must be close to each other. For what? For the same thing. You get this kind of loading pattern from this one, okay, to produce the maximum moment loading case 1. And this one come from this one. Okay, this is going to produce the maximum moment. And then this one is for the for the inference line diagram of the mid span of the beam. Okay, and then from this you will get the live load W loading pattern like this. The load here is dead load. Okay, dead load always hold the span. After analyzing different kind of cases, okay, they get the coefficient for maximum moment. And then for this coefficient, they just put into the C sub M for the moment. For the shear, they will get this one for C sub E. Okay. When you study the reinforced concrete design, Ajahn who lecture the reinforced concrete design supposed to give you more detail about this. Okay, for this course, we get this one. It depends on the type of support. Okay, that's we consider. If this end is unlisted, okay, and like the wall, and then you put the beam on the wall like this, no connection. So the moment coefficient over here is 0. This is 1/11. And this one is negative, like I told you. In the support, it's going to be negative. And this is going to be negative. And this is going to be positive. Positive occur at the midspan. Negative occur at the support or the column. Okay. If the connection is the beam, okay, if your beam is connected to the bigger beam like this, so the C sub M here is -1/24, and then the redistribution of the coefficient gonna be something like this. And if disconnected to the column, this is the column, okay, this is connection to the column, and then you can see the coefficient change to different kind of value. And then you can use this kind of coefficient in the analysis of reinforced concrete beam by the ACI. Next, I have the more example that more comprehensive than this one. Okay, but this one I like to give you guys an example to work on. I have about 10 more minutes. Okay, let me show you how to draw the inference line diagram a little bit further. Let us move to this one. Okay. From the previous one, what we have is the pin roller. This one, I just check it into pin roller and fixed. Fixed support have some kind of spatial effect. Okay, when this one end is the roller, it can rotate, but when this one is fixed, it cannot rotate. The slope at the fixed end is 0. So this is going to be the spatial thing. Okay, fixed. The slope here is going to be 0. Okay, compare this one to the previous one. I just change this one to the fixed. Okay, after I finish these two examples, this one, and this one, you have the assignment. If I have fixed, what's going to be? Okay, also explain the Musler-Besler principle. Can you explain the benefit to finding the loading pattern, for example, of the inference line diagram? Okay, I think you guys can do so. Okay, let me draw the inference line diagram of R sub A. The same thing. This one is going to be roller, and this one is fixed. What I'm going to do is I'm going to release this one to be the roller here, and then I put this force to move this one upward for 1.0 unit. When this one move to 1.0 unit, what happened is this too much. This beam gonna rotate, deflect like this. Okay, and this one gonna be downward, and this one going to be upward, and then due to this is fixed, this one going to have the inflection point, and then this portion going to be concave upward. Okay, it's different from the previous one. For the R sub B, this here, this one going to be the same, this one going to be the same. Release the roller, just put the force here, and this one is fixed. This one going to move up, okay, to this position, and for this one is going to be curved like this. For this one is can be curved like this, but the curve must change due to the theta here is 0. So this one is concave. Clearer than the previous one. Concave upward. Okay, and this portion just link it like this. Okay, they're going to follow each other in the same pattern. This is going to be inference line of R sub A is equal to the deflection at point X when the force applied at A divided by F sub AA. This is going to be the inference line of R sub D, which is going to be F sub X when the force applied here at point D, and then divided by F sub D. Okay? For the M sub E, this is M sub E. This is M sub E. Just have this one as the pin, roller. When you put this one to determine the moment at point E, you got to what? You got to put the hinge here. And then there is the moment applied here, another moment applied to the wall, produce nothing. Over here is going to produce the relative rotation of 1.0. And then what happened is this one supposed to be deflected in the shape something like this. Okay, and important to spell out over here. Spell out over here to be 1.0. And then it's going to be inference line of M sub E equal to deflection divided by slope. This is deflection at point X due to the moment applied at point, M sub F at point F. Okay, F. Okay, point F. If just check it a little bit, okay, at point F, this is going to be alpha sub F. Okay, and then if you prefer to have the V sub B,
Okay, you got to have this one, this one, this one, and this one fixed. V sub B, that means you got to put the roller here. Okay, and then put the force of V sub B here. And then this one gonna move this one like this. Okay, like this. And then over here is going to change the curve like this. Change curve like this. Since this one has the angle here, the slope here must be in parallel, and then the curve going to be like this, and the total of this is going to be 1.0. You get the inference line of V sub B equal to the deflection divided by deflection at point X due to the force SB, and then divided by F sub BB. Okay. And then let me move to the M sub E. M sub E. For previous one, M sub E. Just put this one. Okay. And then change this one to the pin and apply the moment M sub E. This one gonna lift up like this. And then this one gonna change the shape to here. 0, theta equal to 0. The author gonna be very simple. The basic thing, slope here gonna be 1.0, and this one must move into this way and this way like this. Okay, so this is going to be the moment M sub E, and then moment M sub F. Let's change this one to be moment M sub B. Okay, sub B, and then you put what? You put the hinge here and put the force like this. This is going to be move here, and then this is going to have the deflected curve. Okay, like this, and then over here the slope just change. This is going to be the inflection point. This is going to be the inflection point. You got to indicate the inflection point, and then the slope here is going to be 1.0. Okay, last one, R sub F. This is going to be the support. This is pin, roller. When we put the reaction upward is positive, release the resistance to R sub F. That means you got to put the roller guide, and then you got to put the force of R sub F to move this one, for what? For 1.0 unit. But anyway, this one still has the moment resistance. So this one will have the shape something going to be like this. Okay. So you get this one for the reaction R sub F. Okay, R sub F. And then this is going to be Im of R sub F equal to deflection at point X due to the force at F divided by the deflection at point F due to the force at F. Okay, so this one go back and trying to push it together. Then the R sub D. R sub D has, this is the big portion, right? So the positive is bigger than the negative. Negative is here. So it's very simple to put the uniformly distributed live load to R sub. How about M sub E? M sub E is this. Which one? Is it this one? This is positive. This is positive. So for the M sub E, you have this one, M sub E, positive. Okay, and the last one, V sub B. V sub B is here. V sub B, this is negative, this is positive, they are equal. And then we have this one negative. This one negative supposed to be larger than this one positive. Equal. So this one gonna be the one who control the loading pattern. So just put this one over here and then half of this to produce the negative shear at point B. Okay. And that's it for the lecture for today. And we have 5 minutes to 3 p.m. And let me finish our lecture here. Okay, goodbye. See you again on Wednesday. Okay, bye-bye.